One at a time.
All right, let's go ahead and talk about these problems and what method you would pick. So, first one, I did see a couple possible inverse trig. What makes you think maybe inverse trig here? What's tempting to say inverse trig? The square root, and you got the x minus 4. But why is this not inverse trig? The x is not squared. If the x was squared, what inverse trig would this be? It still would not be inverse trig, even if that was x squared. It looks almost like inverse sine, but there's one important difference that it would have to be if it was inverse sine. It would have to be 4 minus x squared. If that was 4 minus x squared, yes, that would be inverse sine. If it was x squared minus 4, you would be out of luck. You don't have a tool to do that one yet. Okay? So what did you say could be a possibility? This is a good U sub. This is a good U sub. Specifically, what would you pick for U? X minus 4, that's definitely inside the square root function, and it's in the denominator. So, and then du is just equal to dx here, so that would be a pretty simple U sub. 1 over the square root of u du. Rewrite that as u to the 1/2, negative 1/2, and you're good to go. So we're not going to solve all of them. I will post the answers to all of them on Schoology at some point here in case you want to try them. They're very good practice problems, but we just don't have time to go through all of them. How about this one here? What methods could we maybe do on this one? This is a good long division problem. Why is this long division? Top degree is bigger than the bottom. If the top degree is bigger to or equal to the bottom, polynomial long division is usually your go-to. If the bottom is higher, that's when U sub will probably be a good option, or at least a good starting place. So this is polynomial long division. Did anyone say something that they thought might work and they're not sure why it doesn't work? Besides polynomial long division? Okay. How about this one? 2x plus 1 over x squared plus 1. If you said U sub, there will be some U sub involved at some point. If we were to pick U sub from the beginning, what would we pick U to be? If there's a denominator, we usually want to pick U to be the denominator, right? What will du be? Oops. 2x dx. So why can't we just do U sub only to start on this one? Because of this plus 1, right? And we can't just manipulate and throw a plus 1 in there. If it's like 3x, then that would be fine, right? You can multiply by 3, but we can't just do that. So we have to split it up first. So split up. Then this U sub will work on this part. The one we just specified, right? Now that's 2x. I guess I should have split up my dx too. Left that off, being a little lazy. And then what would I do with this one? Yeah, that's inverse tangent. X squared plus a constant in the bottom is going to be inverse tangent. Next row, this one is a product. If you're looking at a product of 2, there are usually 2 go-to options. U sub and another one. Anyone, what'd y'all pick for this one? This is a good integration by parts problem. This is not going to be a good U sub problem because if U is negative x, D will be negative 1. And we have an x out here, right? So that's not going to be a good U sub one. If it's a product, those are usually your 2 best go-to options, is U sub or integration by parts. If we use integration by parts here, what would we pick for U? 3x. Exponential should always be your last resort for U. So dv would be e to the negative x. And then you would continue using your integration by parts rule. Is this a good u-sub problem with u equals x squared plus 9? It's a good u-sub problem with u equal to the denominator. Why would that cause a problem? Because if this is u, what's du? 2x. Is there an x in the top? No. So we have a problem. What would this be then? This is inverse trig, specifically which one? Inverse tangent. And if u is x, du is just dx, and so it's a very easy inverse tangent. A is 3, so this is inverse tangent. And you could literally do this one real quick. You could pull out the 4, 1 over 3, arctangent of x over 3 plus c. Because u is x, du is dx, and a is 3. So you don't really have to mess around with that one too much. Just pull out the 4 in front. So I guess we will solve that one. Any ideas on this one? This one's a little weird. This is actually a really nice u sub problem, because what it is, if you choose the denominator like we say you usually do with u, what's du? Cosine of x. Well, that's convenient, because what's in the top? Cosine of x, right? So this would literally just be du over u, which is ln of u, which is sine x plus 1, plus c. It's actually a really nice u sub, without much manipulating. How about this one? Yeah, this one's a completing the square. It can't be a u sub, because if u is this, du would be 2x minus 4. Definitely no x's or anything up in top like that. Okay? And if you have a polynomial, it's not long division, because the top is definitely not a higher or equal to power in the bottom. You've got a quadratic like this. This is going to be completing the square. Now, I will confuse you a little bit, because today we're going to solve problems with another method called partial fractions that work on stuff that look just like this one as well. Okay? So if you see something like this, right now completing the square is a pretty easy go-to, because so far if we've had a quadratic like this, that's the only method we've really used, unless we did polynomial long division first. But today we're going to learn another one called partial fractions. And the way that you're going to decide after today which one do you use, completing the square or partial fractions, is if you are able to factor this, that's when you're going to do partial fractions. So could I factor this in? Are there two numbers that multiply together to get 7 and add together to get -4? No, right? So this does not factor, so that's why you'd be forced to use completing the square on this one instead of what we're going to learn today. But just to know, it kind of looks similar. Any questions on that one? After you use completing the square, you're having to use inverse tangent on this one. Most of the time they turn into an inverse trig problem afterwards. Is this one a good u sub? Would this be a good u sub problem? If we picked u, what would you pick u to be? X squared minus 1? What would du be? 2x dx. What is the problem here if we were to pick this as a u sub? The half the du is in the bottom and half of it's in the top, right? The dx is up here and the du is in the bottom. Or half the du is in the bottom. Du being in the bottom is a red flag anytime, right? But especially in this case where half of it's split, right? That doesn't really help us at all. So this is not a good u sub problem. What is this one? This is inverse trig. Which one specifically? Arcsecant. And this is exactly arcsecant. A is 1. U is x. So it's literally just arcsecant of x. And this last one is probably a little tough I think the most common answer I've seen today is U sub. I definitely think that is tempting. What would you pick to be your U if you were going to pick U sub? If we pick U to be x squared, what's du going to be? 2x. Is there a 2x anywhere in there? No, there's an ln of x. So that's not really going to help us. What would be your other option for U? ln of x. If we pick ln of x for U, what would du be? 1 over x dx. That's a little bit closer. But what's the problem with that? It's 1 over x squared, right? That's not 1 over x. It's 1 over x squared. And you can't square du. That would cause problems if you sub. I mean, you could. You could. If you u sub with this, you'll have u times du squared. But I don't know how you integrate du squared. If you have some ideas, you can try it out one day and see how that goes. So this is a problem. So this is actually not a u sub. This is something else entirely, which I agree, it's kind of hiding. It's not something you would expect to use this method on. Anyone have an idea? This is an integration by parts question because although that it's a quotient, you could also think of every quotient as a product. This specifically could be the product ln of x times 1 over x squared. So this is an integration by parts problem. It just is kind of a secret one. Kind of disguises itself because it's not an obvious product. What would u be? ln of x and dv would be not x squared, but 1 over x squared. Because remember, dv has to be what's being multiplied by it, not what's being divided. And then if you do integration by parts with that, it will actually work out quite nicely. Any questions about that one? So I just think this is good to kind of practice thinking about all the methods that we've talked about as we kind of go through, because it can be kind of convoluted, especially when we add a new method pretty much every day. Down here below on the bottom of this page are some summaries of some of the procedures we've already talked about, and then some of the weird tricks that we've talked about, and even a few more weird tricks that we have not talked about. But we are now going to move on to a method called partial fractions for today. So, partial fractions is actually completely algebraic. There's nothing calculus about partial fractions. It's kind of like polynomial long division. Did you learn polynomial long division in calculus, or did you learn it in algebra? You learned it in algebra. Did we use it to solve an integral problem? Sure. But the actual polynomial long division was really algebra based, and then it just put us into some form of something that we could then find the antiderivative of. That's the exact same thing as how partial fractions work. It's a way to break down the integrand, or the part inside, into a set of partial or part fractions. So we're going to take our integrand, or the thing inside. The time when you're going to use partial fractions is when you see the denominator already in factors, or you can factor the denominator. That's when you'll want to use partial fractions. So it's usually pretty obvious when it's time to use partial fractions, either when the denominator is factored for you or where you can factor it. Okay? And every fraction, there's a theorem out there that says we can break up every fraction into a sum of partial fractions. It's proved out there. I didn't prove it. I'm not that smart, but some mathematician did. Okay? And how can that be broken up? Well, this partial fraction, this guy can be broken up into two partial fractions, one for each of the factors in the denominator. So one fraction will have x plus 3 as a denominator, and the other fraction will have x minus 2 as the denominator. If you had an x plus 4 in there as well, you would have a third fraction with x plus 4 as the denominator. And then what the theorem tells us, that's the extra special part, is that each of these fractions will have a constant, we'll call 1a and 1b, of some sort in the top. It is guaranteed that this fraction here, and really any fraction that has a denominator that can be factored, so any rational fraction, can be broken up into a set of partial fractions. Now, in our particular case, the reason why these are constants up here are because these denominators are linear factors. We'll look at an example in a minute where the denominators, one of them is a quadratic factor, and this will not be a constant anymore up here. Okay, but as long as that factor in the bottom is linear, there's going to be some constant. So now our job is to figure out what these constants A and B are. And we're going to use just how we add and subtract fractions to help us do that. So what do I have to be able to add two fractions together? Common denominator, right? So what am I going to have to multiply this fraction by? X minus 2. So I'll multiply A times X minus 2 and X minus 2 in the bottom times X plus 3. And what will I have to multiply this fraction by, the second one? X plus 3 in the top and bottom. This time around, I'm going to write out a lot of steps so you can kind of see the why, but in the future, you'll be able to shorten your steps a little bit and not write down quite as much. And these two fractions should be equal to 5 over X plus 3, X minus 2. Now we can add these two fractions together by adding their numerators. So of A times X minus 2 plus B times X plus 3, since they have a common denominator, that denominator just stays. And this will be equal to 5 over X plus 3 times X minus 2. Now, we have a fraction and a fraction. These two have the same denominator. So if they have the same denominator, what is this numerator going to have to be equal to? 5. So now we've given ourselves an equation. 5 is equal to A times X minus 2 plus B times X plus 3. So we get to kind of ignore the denominators. You'll usually jump from this step to this step in the future, but I want you to understand why you're doing what you're doing. So that's why we're doing that the first time. And now our goal is to find A and B, right? There are lots of different ways that you can find A and B. I'm going to show you some tips for how I recommend finding A and B. But remember that this equation has to be true for every single possible X out there. Every single value of X, this equation has to be true. Is there a particular value of X that you think might be nice to plug into this equation? 1 would be nice, but I think there's some better ones. We'll use 1 later. 2 would actually be a really nice value of X to plug in. Let's see what happens when we plug in 2. We'll have 5 is equal to 2 minus 2 will be 0. So what is all of this going to become? 0. And your A disappears. 2 plus 3 is, oh, sorry, I forgot to say. We're letting X equal 2. For this part. Two plus 3 is 5, so this will be 5 times B. So then 5 will equal 5B. So what does B have to be? 1. Boom. You have found B. Another value of X that you think might be nice to choose? I like -3 because now that's going to make the B 0, and then you'll be able to find A. So we'll use X equals -3. So we'll have 5 is equal to 5 times, A times -5 plus 0, because plug in -3 here, and all of this will become 0. And so then A is equal to -1. And that was our goal, right? We just needed to find A and B. And we have done so. So that is your method of partial fractions. You have found that this fraction here breaks up into 2 fractions. -1 over X plus 3 and 1 over X minus 2. Okay, so that's the method of partial fractions. And so what we're going to do now is do the calculus. So we're going to use this method to turn this integral into a whole new integral. The integral of -1 over x plus 3 plus the integral, or I'm sorry, plus, we won't separate the integrals yet. I want you to see what we're doing. Plus 1 over x minus 2. So this fraction inside breaks up into these two partial fractions because of what we had up there, where a is -1 and b is 1. And the reason why this is so helpful is because now we can do the antiderivative of these separately. I can even pull out the negative in front of this first one. And these are actually very easy integrals now. These are logarithm antiderivatives, or really easy u subs, where u for this first one is equal to x plus 3, and since du would just be equal to dx, then this is just a negative du over u. So this guy will just be negative ln of x plus 3. So you're going to get into the habit that you'll see these natural logarithm ones and not have to actually write out the u sub when they're really nice like this. Same thing here. U could be x minus 2. Du would just be dx. So then this will be ln of x minus 2. And now you have found the answer to the integral. So when you break it up into partial fractions like this, it usually turns it into some nice, easy fractions that we can integrate. Maybe not always easy, but easier, things that we know how to integrate. Any questions about our method of partial fractions or the integration? Okay, let's do another one. So we're going to take our fraction and we're going to break it up into partial fractions. There are two factors in the denominator, so we will still have two fractions. One will have a x minus 1 in the denominator. Another will have x squared plus 1. I have factored all of these for you already, but a lot of times when you'll use partial fractions, you'll see something that isn't factored, and your very first step will be to factor the denominator. But I believe in your abilities to factor, maybe too confidently. This one's going to be a little bit different, though, because what do you notice about this factor right here? It's squared. It's a quadratic factor. It's not a linear factor. So this guy will have just a constant in the top. But the theorem that tells us that we can break it up into partial fractions says that if there is a quadratic factor in the bottom, then the top will be some linear function. So a bx plus c. So you'll have two constants here, a constant in front of the x term and a constant on its own. And you have to do that whenever your factor in the bottom is a quadratic factor. If it's a linear factor, you get to just put a plain old constant up there. So now we'll go ahead and add these two fractions together. This is the part where I'm not going to do the whole adding the fractions together. If I wanted to add these fractions together, what would I have to multiply this fraction by? So I'm just going to multiply the a by x squared plus 1, because I know really all I care about at the end is the numerators. And then what do I need to multiply this fraction by? X minus 1. Again, I'm just going to do the numerator because I know I don't really care about the denominator. Eventually I'll get all the same denominators, and then I'll just set the numerators equal. And so this will be equal to the numerator over here. So it just kind of saves you some writing steps. You are welcome to add in all those steps if it helps you understand what you're doing, but I wanted to at least do it for the first problem, so understand why we were doing what we were doing. Okay, so now we need to find a, b, and c. We now have three constants we need to find. What's the value of x you think might be nice to plug in? I think 1 would be nice because it's going to make this 0 right here, right? And that'll take out B and C and will let us find A. So let's let x equal 1. Because remember, this has to be true for every single value of x. You could plug in anything you wanted. You could plug in 10 if you wanted. But if you plug in 10, you're going to have an equation with A, B, and C in it. And how are you going to solve for A, B, and C if you have all 3 variables in one equation? You can't. So that's why we picked that nice values. So this will be 4. 3 times 1 is 3, plus 1 is 4. This will be A times 2, because that'll be 1 squared plus 1 is 2. And then all of this will become 0, because that'll be 0 times B plus C. So then that tells us that A is 2. Any other values of x that you think might be nice to plug in? So a lot of times what you want to do is look at these factors and see if there's anything that will make it 0. This one, we already used 1. Is there anything that will make this guy equal to 0? You could use an imaginary number if you wanted to. And once we plug that in, the only problem is we're going to have this will go away. But then you'll have 3i plus 1, and you'll have bi plus c times I minus 1. So you'll have 2 variables and 1 equation, which is not really going to get us anywhere, right? 2 variables and 1 equation. 0 actually is a really nice one, because what will 0 do to this? What will happen to b? Poof. And we already know a is 2, right? So if we plug in b, something 0 here, b will go away, a is 2, and all we'll have left is c, right? So we'll be able to find c. So let's let x equal 0. And you'll get 3 times 0 plus 1 is 1. A is 2. We already know that. 0 squared plus 1 will be 1. And then this will be c times negative 1. This will be 0 plus c will give us c, and then 0 minus 1 will be negative 1. So 1 will equal to 2 minus c. So negative 1 equals negative c, so c will be equal to 1. Now that we know a and c, all we need left is b. So if we plug a, c, and c in, we can plug in any single value of x we want out there, right? To plug in for x, and then we'll only have one unknown, right? So what value of x do you want to plug in? 2? I think 2 might be nice. It'll not get too crazy big. So let's plug in x equals 2. So 3 times 2 is 6, plus 1 is 7. A is 2. X is 2, so this will be 2 squared plus 1 will be 5. We don't know b, so this will be 2 times b. C is 1, and then 2 minus 1 will be 1. So plug in any number you want, but the easier the math, the better. So this will be 7 equals 10. Plus 2b plus 1. So negative 4 is equal to 2b. B is equal to negative 2. There are lots of different ways to solve for these constants. Picking nice values of x is usually the best way. If you can do that, you might see other people do other things. There's some nice things you can do. If you want to multiply everything out, you can compare coefficients and see what are equal. Other times you might run into a place where there wasn't another value of x that will cancel out one of these. Like if 0 didn't work out nicely to cancel out one of the variables here, you could always just pick any two numbers you want. Like we could have picked 2 and 3. And if you plug in 2 and you plug in 3, you'll get 2 equations and 2 variables, b and c. And then you could solve for b and c because you would have a system of 2 equations. So those are just some of the other ways that you could do it if you ever run into it. So now we found all 3 coefficients, so we're going to plug them in. So instead of doing the integral of 3x plus 1 over that guy, we're going to do the integral of a, which is 2, over x minus 1, plus bx plus c, so negative 2x plus 1 over x squared plus 1. This one will be an easy logarithm problem because if u is x minus 1, du will just be dx. This guy is almost a good u sub, so let's break this up first into 2 separate integrals. But because if u is x squared plus 1, du will just be 2x, so we'll have to go ahead and break up this one anyway. So let's go ahead and break up this one as well. So here, if u is x minus 1, du will just be dx. So pull out that 2, and you'll have 2 ln of x minus 1. Here, if u is equal to x squared plus 1, now our u sub will work very nicely because du will be 2x dx. Pull out that negative, and you've got ln of x squared plus 1. And what is this last one going to be? That's arctangent. That can't be a u sub because there is no 2x in the top, right? There's no x in the top. So it's not going to be another ln of x squared plus 1. Just always be careful of that when you're checking for logarithms. So this will, and this is just plain old arctangent. A is 1. And then we're done. So usually once you've done partial fractions, you have to use other tools to find antiderivatives, which is why we keep reviewing that stuff. Okay, we are actually going to, we'll see if we end up, we might not do the whole last question. I'll tell you how we started, but I want you to go down to the bottom of the next page, actually, and I just want to show you some examples of how you would create your partial fractions if they looked a little bit different. Okay, so the last one we had was like this: x minus 1, x squared plus 1. So what if this was, instead of a plus 1, so on the bottom of your back page, I want you to write down this example. What if this was minus 1? How would that change this denominator? Oh. How would that change this denominator? What factors do I really have now? Yeah, this is a difference of 2 squares, right? So doesn't this factor even more? What did that factor into? X minus 1, x plus 1. So really, this is 3x plus 1 over x minus 1 squared times x plus 1. And something interesting happens when you break up your partial fractions, when you set them up at the beginning, when you have a multiplicity of your factors in the bottom. So if I were to do partial fractions for this guy, you actually aren't going to break it up into, it might be tempting to break it up into 3 fractions because you see 3 factors, but because this has a multiplicity, you're going to still do 3 fractions. One fraction will have x plus 1 as the denominator. But the way you're going to deal with the multiplicity is you're going to have one fraction will have x minus 1 squared as the denominator, and then one fraction will just have x minus 1. And let's say that was cubed instead. You would have one fraction with x plus 1 in the denominator. You would have one fraction with x minus 1 cubed. And then you would have a fraction for each multiplicity. So x minus 1 squared and x minus 1. This guy obviously just has an a for a constant. It's tempting to say this one needs a bx plus c because this is being squared. But the thing that's being squared is still a linear factor, right? The factor itself is linear. It's not a quadratic factor. So you get to still have a plain old constant above that one. And same thing with the cubic one. Because the linear factor itself is being cubed, all of these would just be plain old constants. You don't have to do the bx plus c thing. Now, I would not give you one that looks like this because that's a lot of constants to find, but it's just kind of good to understand how it gets set up. And one more example here. Let's say it was x minus 1 squared and x squared plus 2 in the bottom. I want you to write down what you think the partial fractions would look like for that one. So you'll have a over x minus 1 squared, because that has multiplicity of 2. B over x minus 1, because you keep going down until you do it like the multiplicity and then you go down. And then the last one is just going to be one fraction for x squared plus 2, because that's just one factor. But what will the top have to be here? Cx plus d. Because it is a quadratic factor, it will need that linear top. So like when you go to multiply, when you go to make your tops here, this guy here, what would you multiply this fraction by to get the same denominator for all 3? And the same denominator is this. You'd have to do this one by x minus 1 squared, right? So x minus 1 and x minus 1. This one, you'd have to multiply just by what? X plus 1, and then this one, x plus 1 and x minus 1, right? So you're still following the same rules, right? It's just going to be a little bit of a different setup sometimes. Any questions about that setup for the partial fractions? Because this is the weirdest part. Okay, this last example on the back page, we're not going to do all of it, but it is a unique example because you would actually use long division first on this one. Because why? Why would we use long division on this one first? Numerator is higher than the denominator, right? So if the numerator is higher than the denominator, we call that an improper fraction, even in rational fractions. So you would use polynomial long division first. I'm just going to tell you what you would get when you do that. When you do that, that would then turn into x minus 1 plus 2x plus 1 over x squared minus x, or x plus x minus 2. Now this part you could just find the antiderivative of. This part here you could technically use u sub on. You don't have to do partial fractions, but let's talk about what it would look like to use partial fractions on this part. So I want you to tell me how you would break this up. For partial fractions. Technically you can do u sub. You don't have to do partial fractions here, but it's good to practice more partial fractions. So this will factor into x minus 1, x plus 2. So you'll have a over x minus 1 plus b over x plus 2. When you multiply, you'll end up with 2x plus 1 is equal to a times x plus 2 and b times x minus 1. We're not going to work the whole thing through, but what would be two nice values of x that you would want to choose here? 1 and negative 2. And then when you're done, you would end up with this integral here. A, you should get 1, and B is 1 as well. So then your final answer here for this problem, if you try it on your own later, if you want to finish it, will be this guy. A lot of times these problems have different methods. Like I just said, you could also do a u sub on these. So sometimes you might see an answer that looks a little bit different than your answer, but it might still be equivalent. Like for instance here, you can combine these logarithms together by multiplying. So like sometimes answers will just look different. So just because your answer isn't exactly the same, make sure it's equivalent.